Dear students, myself Dr. Sangeeta Sharma, Associate Professor, PG Department of Chemistry, Government Rural College, बीकानेर। आज हम MSc फाइनल 9th बी फिजिकल के पेपर होएनबर्ग-कोहेन थ्योरम, जिसको हम HK थ्योरम कहते हैं, पढ़ेंगे। DFT is made possible by the existence of two ingeniously simple theorems put forward and proven by Hohenberg and Cohen. The HK theorem relates to any system consisting of electrons moving under the influence of an external potential V external R. Theorem 1. For any system of interacting particles in a external potential V external, the density is uniquely determined. In other words, the external potential is a unique functional of the density. E n r is equal to integration of n r V external r dr plus f n r. Equation number 1. And equation number 2, E n r is equal to functional psi Hamiltonian psi. The Hamiltonian can be written as H Hamiltonian is equal to F plus V external, where F is electronic Hamiltonian consisting of kinetic energy operator T. F is equal to T plus V E, and V is an interaction operator. Proof 1. Assume that there exists two potential V external 1 and V external 2 differing by more than a constant and giving rise to the same ground state density n r. Obviously, V1 external and V2 external belong to distinct Hamiltonians, H1 external and H2 external, which give rise to distant wave functions psi external 1 and psi external 2. Because of the variational principle, no wave function can give energy that is less than the energy of psi 1 external for H1 external R, that is E1 is equal to Hamiltonian operator psi 1 Hamiltonian 1 psi is less than psi 2 Hamiltonian H1 psi 2. Equation number 3. Assuming that the ground state is not degenerate, the inequality strictly holds because we have identical ground state. Density for the two Hamiltonians, we can rewrite equation 3 as equation number 4. Exchanging label in equation 4, we obtain psi 1 H2 psi 1 is equal to psi 1 Hamiltonian 1 psi 1 plus integration dr V external 2 R minus V external 1 R N0 R. Equation number 5. Adding equation 4 and 5, we get E1 plus E2 is less than E2 plus E1, which is clearly contradiction. Thus, the theorem has been proven by reductio ad absurdum, a method of proving the falsity of premises by showing that its logical consequence is contradictory. Theorem number 2. A universal functional for the energy En can be defined in terms of density. The exact ground state is the global minimum value of this functional. Proof second. Since the external potential is uniquely determined by the density, and since the potential in turn is unequally except in degenerate situation determines the ground state wave function, all the other observables of the system such as kinetic energy are unequally determined. Then one may write the energy as functional of the density. En is equal to Tn plus E internal n plus summation V external R and R plus E2 is equal to En plus summation plus integration V external R and R plus E2. Equation number 7. Where Fn is a universal functional because the treatment of the kinetic and internal potential energy is the same for all systems. In the ground state, the energy is defined by the unique ground state density N1R is equal to E1 equal to En1 equal to psi 1 Hamiltonian 1 psi 1. Equation number 8. By the variational principle, a different density N2R will necessarily give a higher energy. E1 is equal to En1 equal to psi 1 Hamiltonian 1 psi 1 is less than psi 2 Hamiltonian 1 psi 2 is equal to E2. Equation number 9. The variational principle is enable a problem to be solved using calculus of variation which concern finding such a function which optimize the value of quantities that depend upon those functions. It follows that minimizing with respect to nr the total energy of the system written as a functional of nr, one finds the total energy of ground state. The correct density that minimizes the energy is then the ground state density. Approximations exchange correlation functional. The major problem with DFT is that the exact functional for exchange and correlation are not known except for the free electron gas. A free electron gas, a population of free electron in a vacuum or in metallic conductor. However, approximation exists which permit the calculation of certain physical quantities quite accurately. One of the simplest approximation is the local density approximation LDA, where the functional depend only on the density at the coordinate where the functional is evaluated. Local density approximation and equal to E xc n r d cube r. The local spin density approximation LSDA is straightforward. Generalization of the LDA is include electron spin ELSDA n clockwise n anticlockwise is equal to integration EXC n clockwise n anticlockwise n r d cube r. In LDA, exchange correlation energy is typically separated into the exchange part and the correlation part. E exchange is equal to Ex plus Ec. The exchange part is called direct, sometimes Slater exchange, which takes the form EXDN 1 by 3. Highly accurate formulae for the correlation energy density EC n clockwise n anticlockwise have been constructed from quantum Monte Carlo simulation. The LDA assumes that the density is the same everywhere. It has tendency to underestimate the exchange energy and overestimate correlation energy. The error due to the exchange and correlation parts tend to compensate each other to a certain degree. To correct, it is common to expand in terms of the gradient of the density in order to account for the non-homogeneity of true electron density. Thus, allow correlation based on the changes in density away from the coordinate. These expansions are referred as generalized gradient approximation GGA. GGA xc n is equal to integration EXC n clockwise n anticlockwise del n clockwise del n anticlockwise n r d cube r. Generalization to includes magnetic field. The DFT formula described above breakdown to various degree in the presence of vector potential, that is a magnetic field. In such a situation, the one-to-one mapping between the ground state electron and wave function is lost. Generalization to include the effects of magnetic field have led to two different theories: current density functional theory CDFT and magnetic field density functional theory BDFT. In both theories, the functionals used for the exchange and correlation must be generalized to include more than just the electron density. Application. The DFT finds increasingly broad application for interpretation and prediction of complex system behavior at an atomic scale. Specifically, DFT computational methods are applied for synthesis related systems and processing parameters. In such systems, experimental studies are often encumbered by inconsistent result and non-equilibrium condition. It can be for studying the effects of dopant on phase transformation behavior in oxide, magnetic behavior in dilute magnetic semiconductor materials, and the study of magnetic and electronic behavior in ferroelectric and dilute magnetic semiconductor. DFT gives good result in the prediction of sensitivity of nanostructures to environmental pollutants like sulfur dioxide or acrolein, as well as prediction of mechanical properties. KS theory can be applied in several distinct ways. The LDA are still commonly used along with plane wave basis set, as an electron gas approach is more appropriate for electron delocalized through an infinite solid. In molecular calculation, however, more sophisticated functions are needed. A huge variety of exchange correlation functionals have been developed for chemical application. Some of these are inconsistent with the uniform electron gas approximation. However, they must reduce to LDA in the electron gas limit.